Well, good afternoon, good morning, or good evening, depending on where you are in the world, and welcome to today's DevOps.com webinar. This is Charlene O'Hanlon, moderator for today's event, and I welcome you. We have a great webinar on tap today, but before we get started on that, we do have a few housekeeping items we need to go over. First of all, today's event is being recorded, so if you missed any or all of the event, you will be able to access the webinar on demand post-event. We'll be sending out an email link that you can access the webinar. And we're also taking questions from the audience. So if you have a question for our panelists today, at any time, just use your control panel to go to webinar control panel and submit your questions. And hopefully we'll have a few minutes before the end of the event to go over the audience questions. Okay, with that, we'll go ahead and kick off today's webinar. Case study, how to keep your email service humming and GDPR compliant. Learn from the experts. Our expert today is Dylan Ferreira, who is lead systems administrator at FuseMail. And he's going to be joined by Chris Chirillo, who is director of product marketing at Influx Data. Hey, Dylan, how are you?
Hi, not bad. How about you?
Doing great, thanks. Well, listen, I'm going to go ahead and just turn it right over to you and let you go ahead and start with your presentation.
All right then. Hi everyone, thanks for joining today. My name is Dylan Ferreira and I'm a sysadmin at FuseMail. FuseMail is part of J2 Global, which runs a ton of sites you might have heard of, such as Mashable and speedtest.net. And with our FuseMail and Viper product lines, we provide anti-spam and antivirus solutions. I work on the FuseMail side, where we provide email security solutions to small and medium businesses. Our products provide email protection such as anti-spam, anti-spoofing, and custom policy-based filtering where a client can configure mail delivery and routing rules. We provide a host of other services such as email archiving and encryption, but today I'm just talking about our core email filtering and delivery service. So what's on the agenda today? I'm going to take you through a project we started back in July of 2016. So we're going to go through what the project was and what we were trying to do, how we decided on InfluxDB, how we tested InfluxDB, some lessons we learned, and a bug we found along the way, the initial design, the wonders of having raw data, and the use of Kapacitor to satisfy a GDPR requirement. So in mid-2016, we were given the task of collecting email latency statistics for our core mailer. For the rest of the talk, I'm going to, the box outlined in red is what I mean when I say the mailer. This timing is confined to the time it takes for a message to be processed by our mailer. And by processed, I mean scanning, filtering, and routing, all the way to delivery. The requirements are that we keep long-term latency percentile data in daily, weekly, and monthly aggregates so that we can report on our performance and track it against our SLA, review our software updates and deployments for changes in overall performance, and improve our capacity planning. Up until then, we'd relied on queue threshold monitoring to detect delivery lag. Queue monitoring alone will show you when you have a big problem, but as we found out later, plenty of smaller issues were happily bubbling under the radar. And with queue depth, it's impossible to tell the difference between a queue caused by an increase in message rate or a lag caused by an unhealthy service or dependency. So the first idea put forward was that we set up a system to periodically send probe emails through the platform and catch messages on the other side, storing the data on the time it took these messages to be delivered. To send probe emails, we need to have something on the outside of our network to generate email. We need configs in our production service to receive and route that email. We need something on the other side of this to actually receive the email and generate metrics data. And we need something to clean up any artifacts created by these steps, because this sort of thing doesn't always work perfectly. But the mailer is a routing and filtering engine, and there's more than one path to a delivery. The problem with this kind of monitoring is that no matter how many routing configs we add, we either end up with a small set of message types passing through routing configs designed specifically for them, or a system overloaded with probe messages. And after all this, your users have a habit of finding unexpected ways to configure and use your service. So your users may be struggling while your dashboards all look green. Plus, any monitoring you put in place is going to require ongoing maintenance. So it comes down to where you want to be putting your time: finding and fixing production issues or maintaining your probe configs. We use similar setups over the years, and I've always found probes to be fragile. You end up having to maintain a whole bunch of probe routing configs. There's way too many paths through the platform, so these paths are always changing as features are deployed and modified and retired. And if you go this route, your probes add extra load to your service, and now you're affecting your service. So the result of this is that you have lots of new stuff to manage. You're always going to get just happy path testing, and because of this, your metrics are mostly useless. A limited set of probes is necessary to give you confidence that your service is up and available, but users have a habit of finding ways to use your service that you haven't anticipated, so measuring their experience is essential. So why not measure the actual production traffic? So here's where we got some lucky timing. Right around the same time we were assigned this project, our mailer team was working on building event logging directly into our mailer. The mailer would publish information on deliveries into NSQ for consumption by various services. NSQ is a simple distributed message bus. You can publish any kind of content into it, raw text, JSON, or whatever you have, into a topic. And one or more consumers can create channels and get a feed of that data. So it wasn't a great leap to see that we could tap into this and gather stats on our production traffic. The mailer team kindly agreed to add high precision timing data to the payload. So by using the actual production traffic, we didn't just get richer, more accurate timing aggregations, but we also got message counts and effectively a new form of logging that allowed us to zero in on customer experiences. So how do we store this data? FuseMail's been around for nearly 20 years, and historically we're an Nagios shop with Graphite StatsD setups to store perf data and application metrics data. In 2016, we were starting to move most of our metrics data over to Prometheus, with Grafana as a front end, so we had a few choices. But having worked a little with Prometheus, it was hard to get motivated to stand up a new Graphite project. Prometheus, on the other hand, is aggregated by design, and the log of events from our mailer provided us with a wealth of data. So enter InfluxDB. We had investigated InfluxDB in the early days as a storage solution for another logging project, so we knew it was fairly capable. And with InfluxDB, we had the benefits we saw in Prometheus with the tagged metric system, without the trade-offs of immediately aggregating. And on top of this, we could store multiple fields per row. So lots of useful context could be stored along with the metrics. We still use all three of these systems, and they all have their place. StatsD Graphite is a great setup for somebody that just needs to quickly add some kind of ad hoc metrics data to a batch job or a cron job of some sort. You can easily add a block of code that sends out a UDP payload from any language, even Bash. And once it's set up, it's basically fire and forget, and it requires no forethought about databases or aggregation schemes. Prometheus, we're using this for all of our base hardware, OS, and application metrics. Used in conjunction with service discovery, we found it to be super low maintenance. We keep our alert rules and aggregation rules generic, and new hosts and services require little to no effort to integrate. They're just automatically monitored. Federating subsets of this data into new Prometheus instances is also super easy. So if you provide the access, then developers can have their own subset of the data coming straight to a Prometheus instance they control so that they can do stuff with it. We use InfluxDB when we want to record every single event as a separate data point. Application errors are a great example. Having a Prometheus error counter in your application seems like an easy win until you experience your first error and realize that a rate on a counter that went from null to 1 is 0, and you can't alert on that. And even if you can, why do you want to treat your application errors in terms of rate per minute, or any rate at all? Every event in your application should be treated like, or every error in your application should be treated like an event. The maintainer of this is going to want to see a complete log so that they can identify the cause. So why not have your application fire off an event to Influx? This data, you can then just put straight in a dashboard. There's lots of opinions on these metric systems, push versus pull, and etc. But I believe that it's really all about finding the right fit for your services and for your teams and how they want to use it. So I had some time before the event log project was complete. So I used that time to set up a test rig and get some comfort with InfluxDB. I wanted to find out things like how fast could I push data into the database? How much storage am I going to need? Look at the schema design and cardinality. How much cardinality could I keep? And what things did I need to keep as fields? What the optimum config would be for this data? and what the impact of continuous queries and aggregation queries would be while it's under load. So I wrote a producer in Go to write rows with random values into InfluxDB to get an idea of how much load the database could take. The producer has a configurable cardinality, rate, and concurrency, so we could just dial up the pressure on influx until we overwhelmed it. We quickly learned that InfluxDB is much happier ingesting larger batches, so I started playing with data rates and batch sizes, eventually deciding on a maximum of 8,000 entries per batch. I switched from random to incrementing field data when I needed to audit for completeness and correctness. So the idea for this talk came from a conversation I had with Chris from Influx. I met Chris last spring at Graphanicon. If you attend conferences like Graphanicon or Monodrama, between talks, you'll find me hanging around a few key vendors getting advice on problems I'm trying to solve. On this trip, I had a ton of questions about Kapacitor. This year, Graphanicon was in Amsterdam, and I'd mentioned to Chris that I'd be stopping in Iceland on my way home to see the site, so she wanted to see some photos. So here's a photo from Iceland. It's basically reminding you that you can't see what's coming over the hill in front of you, and this is a good reminder as we enter the test phase. We did run into a few unexpected snags. So in my head, I was still thinking in terms of statsd, so I was pushing data into InfluxDB via UDP. Especially in the early days, I wanted my project to fail in such a way that it didn't impact production in any way, so I used ephemeral NSQ channels in UDP. We treat most metrics projects in our company like this. We want to be able to get metrics, but we don't want the metrics to impact our performance. So this graph shows a per second ingest rate into the database. The data is coming from a test script, so it should contain, or it should maintain, a constant 900 samples per second, but it's occasionally dropping. I checked my test script logs and found that it was producing data as expected. So what's happening here? Was something wrong with Influx? No, this was just UDP. Anytime the host was under pressure, I saw data loss. I'd seen a talk by Joe D'Amato of Package Cloud where he detailed the many ways that the kernel will give up on UDP, making the point that you can lose data with sometimes impossible to detect CPU spikes. The screenshot above shows the impact of a not so great maintenance job running in another container on the same host. Note, we're only seeing drops with no corresponding spikes, so we know we're losing data here. I realized this approach was doomed, so I switched over to the HTTP API. Continuous queries. The documentation describes continuous queries as InfluxQL queries that run automatically and periodically on real-time data and store query results in a specified measurement. I got my feet wet with continuous queries by adding simple aggregations to get ingest counts, because selecting per second counts on high-res data across long time spans was interfering with my tests. The data in this graph comes from the same test producer I used in the last slide, producing 900 samples per second, but now I'm using the HTTP API. But there's a problem. I added the CQ shown at the top, where I calculate a per second rate once every 5 seconds, and I noticed a strange repeating pattern in the data. So the graph above is showing a per second ingest rate of the data. The green line is showing what the actual per second rate is calculated with a query across this entire time span. The blue line is showing the output from the continuous query. So after staring at this for a while, I realized I was seeing a combination of two issues. The first issue was the CQ was racing and beating the ingest data. So with InfluxDB, you have the option of sending a timestamp in or having Influx generate a timestamp for you. And I was taking the timestamp from my message delivery times because that's what I wanted. The problem is between the time I generate that timestamp and the time that it goes to Influx, there's a little gap. And you can see that gap actually on the leading edge of the green line when you do that query right there. That's the same thing. So the second issue was that I was posting into InfluxDB in batches, and the post interval didn't match my continuous query interval, and a repeating harmonic was created from this mismatch. Now, you won't actually see this mostly in longer or lower frequency continuous queries and lower frequency rates. But it's kind of good to get a feel for stuff with high frequency rates, because you can see that you are missing stuff. And the longer the frequency, the less you'll lose and the harder it will be to detect. So this test was kind of good. My batch posting interval was difficult to adjust, as it's not a straightforward interval. There's also a max batch size element to my posts. So it'll either post when it hits 8,000 entries, or it'll post after a certain amount of seconds. And if you have a high frequency of traffic coming in, then you'll end up posting more frequently. So the batch time is kind of variable in the producer or in the consumer. So I modified the continuous query, adding an overlap. So here where it says resample every 5 seconds for 10 seconds, this means that I'm taking a 1 second rate every 5 seconds over the last 10 seconds, and I'm overwriting the 5 seconds of data from the previous continuous query to correct for the race. This, of course, won't work if your latency is higher than 5 seconds. I mean, this is more of an example. And in the real world, if you're doing like hourly rates and stuff, you can go back and do 2 hours, or hourly aggregations. You can do 2 hours, and that will most likely cover off the little bit of latency between the time you produce data and the time it gets written. Modeling your dashboards early. So just like building UIs, building your dashboards helps you, if you build those first, it helps you understand what kind of data you want to collect. So I went through a lot of different dashboards and added a ton of panels and then stripped them down and tried a bunch of things until I had an idea of the kind of data that I wanted, and I could pass this past my managers and see if they were, if this was along the lines of what they were hoping for. And by doing that, you get an idea of what kind of metrics you need to collect. So you can go back and you can start storing your data in the way that will make it easy to get this information or these aggregates. So the same goes for mock data. It helps to test with data at known rates and known cardinality. The test above was generated with random field values, and this data helps me create my initial dashboard and just show it off. Here's what it looks like, and get the continuous queries right, etc. Once I'm happy with that, I switch to incrementing field values, which will look terrible in this. They'll just be a line that goes up forever. But it's easier to audit the data and make sure that I'm getting all my data. And then I found a bug. So while I was auditing some early live data, and this is all the way back in 2016, this is actual event log data from the production mailers that I was using, and I noticed some weird stuff in my graphs. I found negative latency numbers, and I'd love to achieve negative latency numbers, but I suspected we had a problem. So I put a ticket in with our mailer team to check their event log code, and they had audit logs containing all the raw event log data, and we weren't seeing any negative numbers there. And I thought, it can't be NSQ because it's just a message bus and it doesn't understand JSON. And so why would it modify just certain elements of my JSON? But in any case, I added more debugging and logging to my consumer, and all the values being produced were matching the values that the consumer was trying to write to InfluxDB. So the whole message bus stack, producer, message bus, and consumer looked right. So could this be InfluxDB? I found someone reporting a similar issue online, and in that report, it indicated that the problem wasn't confined to just negative values, but some of my positive values could be wrong as well. And by comparison, those would be really hard to spot. There was a pattern with these anomalies, though. They all occurred while I was replaying data into the database. So anytime I was running the same data into the database concurrently, I found I was having these problems. So I started working on ways to reliably trigger this. The test I put together inserts rows in batches of 8,000 with a precision of 1 second to encourage collisions. So pretty much every 8,000 row batch has the same time offset exactly. The rows contain 3 fields: batch counter, an incrementing number once for each 8,000 sample batch I post, and a counter 1 and counter 2 containing a per sample incrementing number by the same incrementing variable. So the idea here is that counter 1 and counter 2 should always match on insert and should always match in the database. When running the attached test concurrently, I ran 10 workers against the same database. I found a small percentage of my resulting rows showed a difference between counter 1 and counter 2. So a simple select star from database where counter 1 not equal counter 2 pulls out all your errors. And I filed this issue with Influx, along with all my test code, and the Influx team verified that this was a known and expected race condition when the database was being abused like this. In reality, this wasn't a huge issue for me because I had no intention of doing this. It was just good to know. And what it boiled down to basically is if you're overwriting a single time series at the same time offset with concurrent connections, the resulting field data could be wrong. Once Influx released the new TSI, I wasn't able to reproduce the issue, and I looked up the original tickets and found that it was confirmed to be fixed. So View 1.1 fixed it. That's ages ago. Anyhow, it pays to test your metrics. So every time series database and every metrics collector has its own strengths and limitations, and they all have subtle behavioral differences. And it's important to understand what they are. Knowing and understanding the potential problems of the solution helps keep everyone's confidence up about the output of that solution. So it really doesn't, it's not that big a deal if you have problems, as long as you know what they are. So what we have so far is our mailers are producing event log data into NSQ. And for prototyping purposes, we can rely on NSQ tail to consume the data. NSQ tail is just like regular tail, but it's for NSQ. And it just hooks into an NSQ topic and takes a stream of live data and returns it to you. If we need to transform or pre-filter that data in any way, we can pipe it through JQ. I often use JQ to add context, like what data center I'm in, so I don't have to ask everyone creating event logs to add this awareness into services which otherwise don't require it. But to work with JSON formatted data, I needed a simple piece of glue, which I called JSON to Influx, to complete my prototyping toolkit. JSON to Influx takes a stream of JSON payloads on standard in, coming straight through NSQ and through NSQ tail and through JQ. And then it uses a config to mark elements in the JSON as tags and fields. Tags have a simple one-to-one assignment, and fields are more complicated in that we need to cast it to a type because you can have various types of field data. In the target section, we configure a DSN with optional batching parameters. If the JSON or if the data that I'm writing is critical, then I write a dedicated consumer with proper retry requeue handling on the message bus because this prototyping rig can be leaky if things get chaotic. But often I find that this rig is good enough for getting any kind of ad hoc data that we're interested in, especially if we're going to do a release of software that we have specific interests about that software or the event logs coming out of that software. It's easy to set up something really quickly with just a little bit of bash. If I need to write a dedicated consumer, I just take the JSON to Influx code and the config that I'm working with, and that's a template that gets me a final product. All I have to do is add the NSQ consumer piece to my code. So I'll refer to this part, NSQ tail, JQ, and JSON Influx as the consumer as we move forward. So what I wanted to emphasize with this slide is that pretty much everything I'm using here is off the shelf. I just had to write a little bit of glue to make it all work. And actually, Telegraf now can handle all of this as it has an NSQ consumer built into it. And you can transform JSON also straight inside Telegraf. Unfortunately, the Telegraf JSON transformer can only handle numeric fields. And for this project, we wanted to be able to store things like UIDs, message IDs, IP addresses, things that we needed as strings. So here we had version 1.0 of the email latency setup. The initial setup looked like this. It was a set of consumers in each DC, and they were batch posting to a set of central influx DBs where the continuous queries handled the aggregations. We dashboard directly from these instances. At the time we created V1, we found that the database couldn't handle the combined cardinality of hosts times customers. There was just too many. The cardinality was just too high and it crushed it. So we needed two database servers, one tagged by data center host name and several other low cardinality, low priority tags, and one that was tagged by data center and customer. But when the TSI was released, I found that a single database could handle everything. This was a surprise, actually, because pre-TSI, I started to run into trouble with a cardinality of around 200,000. But running with the TSI, I have a cardinality of 1.75 million now, and there appears to be a lot of headroom on top of that. So, all right, on to some fun stuff. Let's look at some data. Looking at the raw data over the first few weeks, we started seeing interesting patterns. Micro outages and timeout retry patterns, many of these are in the sub-second realm, but they directed us to underlying config problems, query issues, and hardware problems that went unnoticed by our threshold monitoring. After looking at the raw data for a while, we started to recognize distinct patterns in the data, signatures of specific types of problems. So we would start with the raw data. We'd use the raw data to build a hopefully lighter weight view of like a specific type of problem. And often these dashboards were built from completely different metrics. The raw data just points us in the right direction. Here's a good example of raw data making it easy to spot problems. We're looking at a scatter plot of some early live test data, and each dot represents a delivery, with the y-axis being the time it took to process in milliseconds. Most of the messages are being delivered sub-second, but we have some issues. What the heck are these batches of deliveries at 30 seconds? This was a non-blocking dependency that were delaying deliveries until it hits a timeout. So we didn't expect the raw data to show us stuff like this so clearly. This happened a lot in the early days. We were constantly looking at this raw data and seeing problems that went unnoticed by pretty much everything else. And just to get a feel, or just to get an understanding of this, this is a 1 hour view. And in this 1 hour, we're seeing hundreds of thousands of deliveries. So it's kind of hard to spot this otherwise. So I built a dashboard with this in mind, specifically for looking at these kind of issues, called Warhol-Vision, because it reminded me of his paintings. So its main feature is 4 panels running nearly the same query, but each panel shows data tagged by one of the 4 main tags that this data is tagged with. Direction, inbound versus outbound traffic. Data center, which data center did this traffic pass through? Mailer, which host the traffic pass through? And customer, who does this traffic belong to? So this lets us view all critical dimensions of the data at once, and it helps us quickly understand the scope of an issue so we can get to debugging things faster. It has a configurable high pass filter, so it won't crush your browser when you're looking at larger time spans. This is important because in this view, we're looking at messages that took 1 minute or longer to be processed, and this is only the stuff that is breaking our SLA. If we showed all of the stuff that's not breaking our SLA, this time span would be a lot heavier on our browser, make our laptop hot. So looking at this issue again, this is a scatter plot of raw message latency data. The y-axis is the processing time. And the top panel shows a rate per second. We can see a spike here in the ingest rate of data, the outbound rate basically, meaning more messages were received for outbound during this time. And the timing of that spike corresponds with our issue. So the top panel, so the direction panel shows us that the data was mostly outbound traffic. The DC panel shows that the event took place in only one data center. The mailer panel shows us this was all on a single host in that data center. And the customer panel shows us that the message all belonged to one particular customer. So this traffic was pretty much all just one customer sending a lot of outbound. You'll notice that although the issue was caused by one customer, it had significant impact on other customers being processed by the mailer, as that little rainbow geyser coming out, data points coming out next to the red shows. So this kind of event is basically like a huge batch email that goes out and hits one mailer with a ton of recipients and causes some problems. When using InfluxDB with Grafana, you get something called an ad-hoc filter. And this lets you narrow your view by building a set of filters against your data. And this is super handy because when you're looking at stuff like this, you can then take a look at the customer number, which you can't see here, unfortunately. Sorry, it's blurred out. But you can narrow down to just that customer, and then you could lower your high pass filter, and you can see all of the traffic by that customer, which will be a lot less and easier on your browser. And you can get a feel for what the customer is doing otherwise. If this is well outside of their normal usage, then you can do something about it. So we started off looking into probe messages, but because we went with the measure live traffic route, we had a ton of data, and we started using this data to debug our environment. Now, sometimes we looked at the scatter plots for too long and we started to see things. So I'd seen this speaker at Monodirama, and he loved making pictures out of his graphs. And so when I saw this, I immediately thought of him, and I tweeted it over to him, and he seemed to like it. Anyway, this is when you know that you need to take a break. So when I began this, I thought I'd be spending a lot of my time figuring out how to get the data into InfluxDB efficiently, but that was not too difficult. And once that was taken care of, I found myself spending a ton of time looking at the data and finding new ways to express it. So with the ability to add fields, I kept finding interesting and sometimes novel things to graph, like a breakdown of SMTP sessions connecting to us by protocol, or this histogram view. The bottom panel is a good example. This shows a filtered hourly view of the slowest delivery times by customer. Having this kind of data available makes it easy to spot potential problems. Sometimes it's a routing and filtering config problem. Sometimes it's content issues because we're an email company and we get highly variable content. Sometimes it's a database or a host has some problems or a hardware issue. But having stuff like this is great because we can put it up on a TV in our office and everybody in the company has a chance to spot an issue and start asking questions about what's going on. So we have quite a few TV dashboards up in our office now, and we find them super handy. Everybody in the office, as they're walking by, can spot a problem and start saying, what's going on with this red one at the top? So on to Kapacitor. Influx Data describes Kapacitor as a real-time streaming data processing engine. And we've been using Kapacitor at FuseMail for about a year. We've been pushing event log data into it from various services and writing tick scripts to filter and aggregate that data down. So although it's largely considered R&D work, we're using it to spot anomalous user activity in hopes of finding abusive or use or compromised accounts. In this case, we're pushing data directly into Kapacitor, as it's built to accept influx line protocol, just like Telegraf and influx is. This kind of works, but for high cardinality data, I find it eats up a lot of memory, so you got to be careful about what you put in there. So far, I've been happy with this as a way to explore and prototype. So things like sending exam log data into this thing, and then counting things like the number of recipients by sender address, counting IPs that a sender is coming from. Super handy for spotting accounts. If you see somebody sending out of a lot of different IPs, you can be pretty certain that it's a compromised account. So to review our setup, we had a model where in each data center, mailers publish event log data into NSQ. The consumer takes a feed of this data and batch posts into a remote InfluxDB. But we had a problem. GDPR at this point was just around the corner, and we couldn't export personally identifiable information out of a user's region. Personal identifiable information includes information like email addresses and IP addresses. In our case, we're an email company, so pretty much all of our logs contain personal identifiable information. So we have to be very careful with that. Our model requires that all data gets pushed back to a central database to be aggregated. So that's not going to work here. So we redesigned our setup using Kapacitor. In this model, we write all of the raw event log data in HTC to a local InfluxDB. And then we use Kapacitor to perform batch queries on this data, creating local and central aggregations. The per DC influxes can have richer data, but with tighter retention policies, while the central InfluxDB gets higher level aggregations and gets to drop the personally identifiable data for long-term storage. So we still get our long-term metrics and an ability to dashboard a bunch of stuff, but we don't need to keep all of that PII centrally. And we can put stricter retention policies on things. So a bonus of this is that it scales better, as the per DC databases now just have to take in the data from that data center, and the central database only has to cope with ingesting the long-term aggregations. So at this point, our central InfluxDB that we store these aggregations on, I store a whole bunch of other data on there as well, because that database isn't breaking a sweat. So in this model, sensitive data doesn't have to leave the DC, and we still get our long-term percentiles. I ran into a problem with this model, though. We ran into network connectivity issues between one of our data centers and the central InfluxDB, and I found the capacitor was dropping, the capacitor posts to my central InfluxDB were getting dropped. So this is where I end up hanging around at conferences and pestering people at the Influx booth, and came up with a plan to deal with that. And the plan ended up being that I would add a Telegraf instance between Kapacitor and Influx, and make use of Telegraf's buffering. So Kapacitor then just writes Influx line protocol into Telegraf, and Telegraf is configured to have a large buffer that will store any aggregations coming out of it, and it will just keep retrying until that database is available and it can write. So this worked great. I have to be honest that this version of this V2 version, we planned to do this before GDPR became an issue. We originally just wanted to do this to make the system easier to manage and scale. And with this, it's super easy to just add more aggregations whenever you want by adding tick scripts to the capacitor config. So tick scripts, there's batch and stream. What's the difference? Batch scripts are effectively the same as continuous queries. So in this case, all of our continuous queries that we had in our V1 just became batch tick scripts. Stream scripts are where you can actually take a live stream of the data and that's coming into the table and do aggregations live on it. And for things like that, I'm using a stream script, for example, where I take a sampled subset of the live latency data. I just take the latency figures themselves, and I take like one out of every 10, and I send them to a central database, and I use that now to build my histogram data. Yeah. So the moral here is make use of Telegraf as a buffer, or you might lose your aggregations if your target is temporarily unavailable to capacitor. And while you're using Telegraf, you can configure it to do things like send your data to multiple targets. So now you can have multiple Influx databases, and you can have a little bit of redundancy there. I mentioned that I was using Telegraf as a buffer. I'm also using it as a router. So in the agent config, you can configure a buffer size, and that buffer will be allocated to each output config. And if, like I said, if Telegraf is temporarily unable to talk to the target, it'll queue and retry until it's successful. Super good. I'm also using Telegraf to route the data coming out of capacitor, and I do this by adding a static tag to the output of my tick script. So you can see those in the lower left or the lower right box in purple. I'm just adding a static tag that's called Telegraf route, and it says remote timing 30 days. This is just a value that ends up being a routing config. You can see in the middle right box is a Telegraf routing config, and it's actually stripping the tag before it goes to the target database, and then it filters based on that. So the important thing here is I'm adding a static tag. I'm then routing based on that tag, but I strip the tag out before it goes into my InfluxDB because I don't really need it there. So with this, I can do more with my capacitor outputs, and it requires less capacitor config changes. So now I can store data in more than one database. I can send the data out of Telegraf JSON encoded back into NSQ and have it consumed by some other downstream automation. I'm not certain that this is an intended use of Telegraf, but I found it handy all the same. Recently, when I was speaking to some Influx folks, they seemed a little concerned with how much routing I was doing inside Telegraf and said really I should be splitting that up. But so far it's been working good. And in any case, I recently learned about another project called Influx Spout. This is built on NATS, and it's a purpose-built Influx line protocol router and filtering engine. So I'm investigating this now as a potential alternative. So we've used the same pattern of publishing event logs into NSQ into a consumer on several other projects, with one of the most useful being health metrics on the thousands of automated periodic tasks that run in our environment. This view here is a 5-minute view, and it's showing about 40,000 events. So anytime a cron job, it's basically just a wrapper, and anytime a cron job completes, an event log is published into our message bus that has information about how long it took and what the success was, and that data ends up getting put into an InfluxDB, and it helps us spot things. It's super useful also for being able to locate some kind of maintenance task. If you have a bunch of them through your environment on only specific hosts, you can find where they've been running. So once you get into the habit of writing services that post event log data into a message bus and you put together a tool set like the one I described, it's super easy to set up temporary ad hoc view of anything in your environment. I had to throw a panel in about Syslog Metrics because about a month ago, Telegraf 1.7 was released, and it came with a Syslog input plugin. And I just had to say it's super awesome. Pretty much immediately, I set it up in our production environment and started spotting stuff. Logs are broken down automatically. Basically, you just configure your syslog or our syslog to relay metrics as though it was a remote syslog target straight into Telegraf, and then Telegraf posts that data into an Influx database. And the logs are broken down by application, severity, and facility. And you can add whatever other tags you want, like host name and data center, or whatever's interesting to you. The nightly chronograph builds right now gives you a log viewer, and it's super easy to then just go in and search for stuff. You can narrow stuff down by tags, and then you can just do keyword searches on your logs, and I find them super fast. So I actually replicated this dashboard in Grafana because we'd like to keep all of our tooling for all of our staff available in Grafana, so anybody can go and look. And that works fine too. It's very easy to set up a keyword search type of thing there. So stuff I'm been finding so far are seg faults, kills. I'm just building tick scripts against this data to locate this. Memory issues, block device issues, network issues. So tons of new stuff came out of that, and it was super handy. I was mentioning to Chris earlier that I've started adopting the philosophy of just working on my low-hanging fruit, and I find that that cool stuff just drops in my lap. Things that I would otherwise work really hard for. This kind of syslog data, I was spending a lot of time building log parsers and managing log parsers and stuff like that. And once this came out, I just ripped all that stuff out and put this in, and it's been great. Anyway, that was the presentation. Thanks for watching. And I guess we can open it up for questions.
All right, let's see here. We have got a couple questions in so far, but if you have a question for Dylan, please feel free to use your control panel, and we'll take a look at the audience questions and hopefully get through all of them. So the first one, you mentioned that everyone has access to the Grafana dashboards. Do your developers work directly with InfluxDB, or with you to gather specific metrics for the code they're working on?
A little of both. So they have the ability to publish event log data, and then right now they work with our SRE team to then take that data and put it into Influx. Eventually, I think we'll probably just have it be a little more seamless. And then the data that ends up being in Influx, that data is then available through Grafana to anybody. So the philosophy in our company is our dashboard should just be available to anybody that is an employee in our company. So everybody from our general manager down to anybody in our company can go and open dashboards and look at them and edit them and do what they need to do. But yes, for publishing directly into Influx, a little bit, but not so much yet.
Okay. All right, great. The next question, your new metrics are now measuring actual production traffic. Was there any concern with that approach with the new dev and ops teams initially?
The concern was mostly could we actually store all of that data, and how much resource would that require? So that was what a lot of the initial testing was involved with, or was focused on, was trying to make sure that this wasn't going to be something that was going to, grow out of the available hardware that we had. So what we ended up with is the initial version was 2 databases. That was a little bit tough. Now we have a database in every data center, and we have a central database that holds aggregates, and all of those are basically sharing resources with other things and not stomping on each other's feet. Mostly we just create dedicated I/O for it, and we don't worry about much of anything else. Capacitor for a while was quite a problem for us, because I was getting a little bit overexcited, and I would throw too much data in, and I would run machines out of memory. So I'm trying to be more careful with that.
Yeah. All right. Okay. All right. Next question. How much data did you end up storing when you started to store the raw data?
You're asking, I guess, how much of a footprint on disk is it?
Yeah, I guess how much data when you started storing all of that raw data, how much was it? I mean, are we talking like boatloads of raw data?
Yeah, I was worried about that. So it's complicated because it all depends on how you set up your aggregations. So what we have is the raw data goes into InfluxDB and into a retention policy that stores it for 8 days, and that just gives us an 8-day view on the nitty-gritty details of what's going on in our environment. And very quickly, Capacitor then just aggregates that data down, and we store those aggregations in much longer retention policies, like 10-year retention policies, effectively permanently on disk. And after a year of that, we ended up being at about 146 gig, I think. So we just gave it a pair of 200 gig SSDs and let it go. And the neat thing was that thing just ran itself. Once I set up V1 or V1.1, it just kind of ran itself, and I didn't think about it for close to a year. And then when GDPR became a thing, I had to go back and take another look, and I was surprised. It was just humming along, no disk problems. It kind of managed itself, but it does pay to sit down and work out what your retention policies are going to be and what your data expectations should be, because it would really suck to run out.
Right. Right. Okay. All right. Great. Let's see. Looks like we have one more question here. If you have a question for Dylan, it's not too late. If you will want to go ahead and submit it using the control panel, and we should be able to get to it. The next question: is your Grafana Syslog dashboard that you built available to the community?
That's something I'll look into, actually, because yeah, it's not it wasn't too difficult to set up, and yeah, I think we can probably publish that one. Okay. I'll look into that.
All right.
Maybe yeah, that whoever asked that, if they want to get in contact with me, I can keep them posted on that.
Okay. All right. Sounds great. All right, and with that, that is actually all the questions that we have. So looks like everybody's going to get a few minutes back in their day. So Dylan, thank you very much for giving us such a great presentation. It was really, really fascinating. Also want to remind the audience that today's event has been recorded. So if you missed any or all of it, or you just want to watch it again, you'll be receiving a link via email to access the webinar on demand. And the webinar is also going to live on the devops.com website, so you can always go there to check out the webinar there on demand. Just go under webinars, and there's a listing for on demand and upcoming webinars. While you're there, please check out all the other webinars that we have listed on the site. Hopefully there'll be a few that pique your interest. Again, Dylan Ferreira, thank you for your time. Thanks for giving such a great presentation.
Well,
we all appreciate it very much. Great. All right, everybody. Have a great day. This is Charlene O'Hanlon signing off. See you next time.
Bye, everyone.